just want to wrap up a couple of loose ends with this chapter. We're talking about some kind of more recent derivative rules and using a velocity graph. So first, finding the derivative. Well, for an exponential function, let's just ignore for a second the fact that it's raised to the 4x minus 1. The derivative is going to be 7 raised to the same thing, 4x minus 1, and then we're going to multiply by the natural log of the base, which was 7. Well, then we have to go back and use chain rule. It wasn't just 7 to the x, it was 7 to the 4x minus 1. The derivative of 4x minus 1 is 4. So we're going to multiply by 4. And that's it. This is it. Okay. There is a log rule, if I can just kind of split this over, where 4 multiplied by the natural log of 7 is the same as the natural log of 7 to the 4th, but that is the only simplifying you can do. 4 will not multiply into this exponential. 4 will not multiply into this 7. It would go in as a power, but you could leave it just like this. Our next example here, we've got a product, and we got 5x. This is our first. Let's make e to the 2x as our second. So we got first multiplied by derivative of the second. Now the derivative of e to the 2x is e to the 2x, and then we got to multiply by 2 because of chain rule. Plus second multiplied by derivative of the first, which is just 5. I could clean this up a little bit. We'll have 10x e to the 2x plus 5 e to the 2x, and that's our derivative. I should just mention there are some really nice things about e besides it being its own derivative. You notice that it's in every term, so it's easily factored out. You know, we could take a 5 and an e to the 2x out and have it be 2x plus 1. And this is a really nice factored derivative version of the derivative for if we had to find where there was a horizontal tangent or something. And I just point that out because in the next chapter that'll be really useful. Here we have a velocity graph. I'm just going to quickly go through the justifications and the how do you know, and I would rely on you to actually go back and give me the intervals. Okay, so because this is review. When is the particle moving to the right? Well, remember, we're moving to the right or forward. That means right and forward are the same things whenever velocity is positive. So from -6 to -4, from -1.5 to 1.5, or about 1.5, and from 6 to 8. So how do you know? It's just whenever velocity is greater than 0. When is it moving to the left? Well, that's when the velocity is less than 0. Negative velocity means we're moving left. So when do we change directions? Well, that's when velocity changes signs. Okay? So let me kind of track this through. So because of positive velocity, it's moving forward, then backward, so we change directions at -4. Then moving forward, so we change directions at -1.5. Then moving backward, so we change directions at 1.5. And then forward, so change directions at 6. So those would be the actual points, -4, -1.5, 1.5, and 6. Now, when is it speeding up? Well, we're speeding up when velocity is moving away from 0. Okay? Let's just talk about that, why that makes sense. So let's say right here, from -6 to -4, here the velocity was 2, here the velocity was 0. Well, it must have been slowing down then. But here, from -4 to -2, it went from 0 to -2. So it's speeding up, but going backwards, or moving left. Then it's slowing down as the velocity approaches 0. Then it's speeding up, then slowing down, speeding up, slowing down, and speeding up. So the intervals it's speeding up from -4, I can actually write these maybe -4 to -2, from -1.5 to 0, from 1.5 to 2, and from 6 to 8. Those are the spots it's speeding up. The acceleration graph. Well, for the acceleration graph, let's start with the linear pieces. Okay, so here you'll notice the slope. First of all, acceleration, I should just mention, remember, acceleration is the derivative, I'm going to write d, of velocity. Okay, that's just my notation. It's the derivative of velocity. So all we're really doing here is drawing the derivative graph. So here the slope is -1, so my derivative would just be a constant -1, just like that. Let me go over to the other linear piece. Here, the slope is constant, and it's just +1/2. So from here to here, it's just +1/2. Okay, like that. Now in this part where it's a curve, with curves I look for where the slope is 0. I start with that, and I mark that because if the slope is 0, the derivative is 0. Then I say, well, here the slope is positive, so I got to have a positive derivative. Okay. Here, the other side, the slope is negative, so I got to have a negative derivative. Now, how negative, how steep you make that isn't overly important, but you just have to show that change there, that it was positive and then negative because the function went from positive slope to negative slope. Now you'll notice these jump discontinuities, and that's okay. I mean, that's what the graph requires. But what that means in my original function, just to go all the way back to the beginning of the chapter, is that at these two spots where we have this jump in our derivative, that means that velocity was not differentiable at those two spots. Okay? Velocity is not differentiable because the derivative shouldn't have jumps in it. But if it does, it just means we had a spot of non-differentiability. We would classify those as cusps. Okay? I could maybe make that note as well. Those would be classified as cusps, and that's why you remember corners, cusps, vertical tangents, and discontinuities. Those are the spots where you won't be differentiable. But that's our derivative graph.